Dear students, today we discuss homogeneous differential equations with constant coefficients. So we consider differential equation L of y equal to a0 into nth derivative of y plus a1 n minus 1 order derivative of y plus and so on plus a n minus 1 y dash plus a n y equal to 0. This is equation 1. When right hand side is 0, then we call this equation as homogeneous differential equation, where a0, a1 and so on an are constants. So this equation is called as constant coefficient differential equation. We discuss general solution of this differential equation in various cases. We need a characteristic equation of this differential equation. So first we define characteristic polynomial. We take a constant r. For a constant r, consider L of e raised to rx. So this function is important, e raised to rx. So L of e raised to rx is a0 into nth derivative of this function e raised to rx plus a1 into n minus 1 order derivative of e raised to rx plus and so on plus a n minus 1 into d by dx of e raised to rx plus a n e raised to rx. Now derivative of e raised to rx is r into e raised to rx. If we take second derivative, then it is r square. Okay, differentiation of r into e raised to rx, it is r square e raised to rx. Okay, if we continue, then we can find that in general kth derivative of e raised to rx is r raised to k e raised to rx. Okay, so we substitute these values in previous step. So this becomes, so e raised to rx will be common, a0 r raised to n plus a1 r raised to n minus 1 plus and so on plus an minus 1 r plus an into e raised to rx. Okay, so this expression in bracket is a polynomial in R. We call this as z of R into R, e raised to Rx. Okay, so L of e raised to Rx is z of R into e raised to Rx, where okay, so this is equation 2. L of e raised to Rx is z of R e raised to Rx, where z of R is a0 r raised to n plus a1 r raised to n minus 1 plus and so on plus an minus 1 r plus an. Now this is very useful in finding solution of given differential equation L of y equal to 0. If R1 is root of polynomial z, then z of R1 is 0. Okay. Therefore, by 2, by equation 2, L of e raised to R1 x is z of R1 e raised to R1 x, and z of R1 is 0. So this is 0. This means e raised to R1 x is solution of differential equation L of y equal to 0. That is differential equation 1. Okay, so if R1 is root of characteristic polynomial, then e raised to R1 x is solution of given differential equation. This polynomial z of R is called as characteristic polynomial. The equation z of R equal to 0 is called characteristic equation, and the roots of characteristic polynomial z of R are called characteristic roots. Now we discuss various cases to find general solution. General solution of differential equation 1, that is L of y equal to 0. So first case is, so general solution depends on nature of roots of characteristic polynomial. So first case is real and unequal. Unequal means distinct roots of characteristic polynomial z of r. So our characteristic polynomial is of degree n. So there are n roots. In this case, we have distinct roots. Suppose that r1, r2, and so on, rn are real and distinct roots of characteristic polynomial z of r. As we discussed, if rk is root of characteristic polynomial, then e raised to rkx is solution of differential equation L of y equal to 0. Okay, so therefore e raised to r1x, e raised to r2x, and so on, e raised to rnx are solutions of differential equation 1. Okay, all these functions are linearly independent. Okay, it can be set easily. So you can have e raised to rjx and e raised to rkx, where j is not same as k, and then find Wronskian of these two functions. You can find that Wronskian is non-zero because rj is different from rk. Okay, so it is easy exercise. Verify that any two such functions are linearly independent. Then in general, we can say that this set is linearly independent. And if we have n number of linearly independent solutions of this nth order differential equation 1, then this form fundamental set of solutions. That means a general solution is linear combination of these solutions. Therefore, the general solution of differential equation 1 is y of x equal to c1 e raised to r1x plus c2 e raised to r2x plus and so on plus cn e raised to rnx. So when we have real distinct roots of characteristic polynomial, say r1, r2, and so on, rn, then general solution of given linear differential equation L of y equal to 0 is c1 e raised to r1x plus c2 e raised to r2x plus and so on cn e raised to rnx. We solve one example. Find general solution of y double dash plus 5y dash plus 6y equal to 0. Solution. So this is differential equation 1. L of y is y double dash plus 5y dash plus 6y, and therefore characteristic polynomial is z of r equal to r square plus 5r plus 6. Okay. Now we find characteristic roots. Characteristic roots are given by r equal to minus. Okay, this is quadratic equation. We find roots as usual. Minus 5 plus minus square root 5 square, that is 25, minus 4 into 1 into 6, so 24 divided by 2. So this is minus 5 plus minus 1 divided by 2. Okay, if we take plus sign here, it is minus 5 plus 1, that is minus 4 by 2, so minus 2, and if we take minus sign, it is minus 5 minus 1, minus 6 by 2, that is minus 3. Okay, so we find real and distinct roots. Okay, so r1 equal to minus 2 and r2 equal to minus 3 are real and distinct roots. As we discussed, the general solution is, therefore, general solution of L of y equal to 0 is y of x equal to c1 e raised to r1x plus c2 e raised to r2x, that is c1 e raised to minus 2 x plus c2 e raised to minus 3 x, where c1 and c2 are arbitrary constants. Thank you.